everybody, my name's Helen. I'm an organic chemistry student this quarter, and today for my at-home lab experience I'm going to be making the Toll House cookie recipe for chocolate chip cookies, and we'll look at the chemistry behind the cookie and what effect each ingredient has on the outcome of our cookie. So first we're going to start with 2 1/4 cups of flour, 1 teaspoon of baking soda and 1 teaspoon of salt, 1 cup or 2 sticks of softened room temperature butter, and then 1/3 cup of white and brown sugar. And then to that we'll add 1 teaspoon of vanilla, my favorite, and then 2 eggs and chocolate chips. So the choice of sugar can influence the flavor and texture of the cookies. So I chose to include both sugars, but specifically brown sugar, because there's more moisture and it's slightly acidic, so it adds to the height and the chewiness of the cookie. And the basic baking soda reacts with the acid in the brown sugar and creates carbon dioxide gas, which makes air pockets in the cookie, which makes it fluffier. And I'll be using softened butter today. The temperature that the butter has an impact on the texture and the structure of the cookie. And when the butter and sugar are combined, air is incorporated into the batter, making the cookie fluffier once they cook. For example, if you were to use melted butter instead of softened butter, then the cookie would be flat because there wouldn't be any air incorporated. And the baking soda also adds to the density of the cookie.
We all know how to make chocolate chip cookies, so now I'll break down the exact sequence of changes that occur in the oven that turn our dough into a yummy cookie. As the dough warms to 92 degrees Fahrenheit from room temperature, the butter first melts, so the dough begins to flatten and spread onto the pan. Butter consists of water and fat, and as it melts, the water is released and expands into steam, rising the cookie. Next, the edges begin to get thinner and set, which is why they are the first portion of the cookie to cook. As the butter melts, the cookie structure loosens, so the water from the butter combines with the baking soda. The baking soda then reacts with the acidic components in brown sugar, creating carbon dioxide that cause the cookie to rise. At 136 degrees Fahrenheit, the salmonella in the eggs die. Next, at 144 degrees Fahrenheit, the egg and proteins in the cookie set, setting the structure of the cookie. The once crumbled up proteins loosen and tangle with their neighboring protein. This entanglement of the protein solidifies the egg and gives the cookie its shape. At 210 degrees Fahrenheit, the water boils away and the cookie begins to dry out and form a crust. The steam then evaporates and the cookie is left behind, fluffy from the air pockets. The Maillard reaction then takes place as temperatures reach over 310 degrees Fahrenheit, which is a reaction between amino acids and reducing sugars, giving it only that toasted flavor accomplished by this reaction. This reaction is famous for its smell and flavor, giving bread, baked goods, and even French fries their signature flavor. At 356 degrees, sugar then caramelizes on the sides and bottom of the cookie, giving it that brown color. The sugar molecules break down at high heat, producing that caramel flavor. After the caramelization takes place, the cookies can then be taken out of the oven to cool. On the baking sheet, they continue to bake as the liquefied sugars cool and harden, giving the cookie more of a crunch, and the cookie loses height as the air inside cools and condenses. So we used white and brown sugar in today's recipe. The difference between these two sugars is that brown sugar has molasses, which increases the acidity of the brown sugar, allowing the basic baking soda to react with these more acidic components and create more gases, making the cookie rise more. When the baking soda increases in temperature, it releases carbon dioxide. The pressure from this gas pushes the carbonate from the hot sugar out, leavening the cookie. We can see another reaction with fire, sucrose, and baking soda called a fire snake, which is shown here, exemplifying how much carbon dioxide is released in this reaction. This reaction was discovered by Louis Camille Maillard, who saw it as a reaction between amino acids and sugars. The first stage of this reaction is the reaction between the sugar and the amino acid, producing a glycosamine compound. The electrophilic carbonyl group on the sugar reacts with the nucleophilic amino group on the amino acid. The N-substituted glycosylamine amine would then go through an amine-enamine tautomerism to produce a 1,2-enaminol. That intermediate would then go through a ketoenol tautomerism to create the rearranged Amadori compound, resulting in a ketone. Lastly, the Amadori compound can react to produce multiple products, which then go on to produce other compounds, each contributing to the color, flavor, and texture of our baked good. Some of these products are shown here. A chemical made in the last step are melanoidins, which are long polymeric compounds that act as brown pigments and give our cookies and other goods a signature brown appearance of Mallard products. Here is another overview of the reaction, showing how first the sugar and amino acid react to produce the N-substituted glycosylamine, which then goes under Amadori rearrangement to produce the Amadori compound. This diagram shows how under acidic, basic, or neutral conditions, the products from the Amadori compound are different. However, they all produce melanoidins at the end, giving our baked good that signature brown color. Caramelization is the last step in the baking process and can only happen once the cookies reach 356 degrees Fahrenheit internally, so make sure you set your oven temperature higher than 350 degrees Fahrenheit so you can get a caramelized cookie. With heat, the sucrose can break down into glucose and fructose. The glucose and fructose then dehydrate and fragment into ketones and aldehyde, which polymerize and create other products. Many furan and pyran compounds are created from the 1,2-enediol product from the glucose and 2,3-enediol product from the fructose. These enediols then create HMF and 2-hydroxyacetylfuran through elimination of water. The small sugar molecules react together through condensation reactions at high temperatures and produce polymers with conjugated double bonds, which absorb light and emit a brown caramelized color. Also, through dehydration, carmelin and carmelin are formed by fragmentation reactions and give caramelized products their unique flavor and sugary smell. Overall, I believe this reaction was a success. You can see the beautifully caramelized bottom and sides, and they have a beautiful brown color from the Maillard reaction, and they were pretty fluffy on the inside. Yum!